Alright, if you take a look at this Pasco car right here, essentially it has a spring embedded in it. So when I do that, it's able to basically shoot its arm out very quickly. And what we're going to do is we're going to use that to basically exert a force on the other car being the red car. Now the red car actually has its own spring as well, so it's entirely possible that I accidentally activate that as well. But even if I do, it's not going to be a big deal. So I'm going to try it in 3, 2, 1. And if you notice, looking at the velocity of those cars, they did move pretty quickly. But what you should have seen is that they should have moved basically in opposite directions at equal speeds. And if you look here, the spring actually didn't activate on this one. So it's pretty clear that this one was the only one that did the pushing. But despite the fact that the blue car did the pushing, what you saw was that the red car moved one way and the blue car moved the other way. So typically, if you push something, you might intuitively expect only that object to move. But what we see is that, while this object does the pushing, it also moves backwards because it's free to move backwards. And so that's what happens on essentially a frictionless surface. Each of these cars are about 250 grams, and right now they're of equal weight. But what I can do is I can increase the weight by adding 250 grams to, let's say, my blue car. And what I'll do if that happens is I will end up doubling the mass of the blue car. So this is now 500, where this is 250. Now they have unequal masses, and let's look at the result. So if I can get it done here, and looked like a good result to me. And what I saw was that, again, this car did the pushing, this car got pushed, but they both end up moving in opposite directions. As far as the speed goes, you should have seen that this should have moved at about half the rate that this did. And so what this is demonstrating is Newton's third law, which basically you guys probably have heard as every action there's an equal and opposite reaction. And then we'll just do it one more time here. Put a 500 gram on there now. Now this is a lot more than this. It's about 3 times as much. And so send it off, and you see that that effect is even more dramatic. It doesn't move forward or backwards quite as much as my red car does. So we got to take a look at what's going on here and also define Newton's third law. So try to get the camera set for me to draw on paper here. Essentially, we're looking at an interaction between two objects, and this is where we get into the third law. Now, as I said before, you've probably heard the third law, at least in layman's terms. Usually they say for every action there's an equal and opposite reaction, but what I like to do is go into the details here, and what we're going to say is all forces occur as action-reaction pairs. What that means is that there's no such thing as an isolated force on its own. Every force that exists in this world has its own action-reaction pair. And these forces are equal in magnitude and in addition to that, they are opposite in direction. Opposite in direction. And then the last thing we gotta make note of is that these forces are acting on separate objects. So we got to be careful here, because sometimes people look at two forces and they think that they are action-reaction pairs when they're actually not. So it can be a little confusing, but we're going to keep it simple right now. Basically, what ends up happening is I have object number 1, object number 2, they're in contact with each other. And what we see is that object number 1, we'll make that the blue car, because that's what did the pushing. And object number 2 is the red car, that's what got pushed. But despite the fact that one did the pushing and one got pushed, we see a force here, F1 on 2, which would explain why this object would move to the right. But we see that this object also moves to the left despite the fact that it did the pushing. So we're going to call this force F2 on 1. And this is our action-reaction pair. So essentially what's happening here is that, let's say for the sake of argument that each of these things, they were a mass of 0.25 kilograms. Both of them were. They were equal masses. Essentially what we're looking at here is we're looking at two objects of equal mass experiencing forces that are equal in magnitude. So if we said that the force here is, let's go with something like 10 newtons. They would each experience a 10 Newton force. One would be to the right on object 2, the other one would be to the left on object number 1. And essentially what we're looking at here is we're looking at two objects that will end up accelerating. So what we want to do is we want to compare those accelerations, and what you should have seen is that basically they had the same speed. Now it should make sense because I've got a 10 Newton force acting on a 0.25 kilogram object here and a 10 Newton force acting on a 0.25 kilogram object here. One moves to the left, one moves to the right. Their speeds are equal. And so what I did in this second demo was I loaded up the mass on object number 1. So I added some additional weight on top of it, and what that did was that increased the mass to 0.5 kilograms. Whereas object number 2, it still was the same 0.25 kilograms. So our second object is half the mass of our first object now. And you know, that spring is just as strong as it was before, so you still get the same force, F1 on 2, being 10 newtons. And then you still get another force here, F2 on 1, the action-reaction pair, being 10 newtons as well. But then what you should have observed was that, unlike this case, where the acceleration on object 1 equals the acceleration on object number 2, at least in magnitude, what we see here is that the acceleration on this cart is not so much. It moved a lot slower now. And that's because it has more mass now. So now you have a 10 Newton force acting on a 0.5 kilogram mass, whereas you got a 10 Newton force acting on a 0.25 kilogram mass. What I'm going to observe here is that A1 should actually be equal to 1/2 of A2 in terms of its magnitude here. And so while they do experience equal forces in opposite direction, they are not necessarily resulting in the same movement. You'll see that the accelerations differ, and that has to occur once the masses are no longer matched. So you saw Newton's third law in action, and then what you can see is that hopefully this demonstration right here clearly proves that, you know, they are experiencing equal forces in opposite direction, and then this one lets you kind of put it in a little bit more perspective once you see the masses mismatched with each other.